So yeah, as Professor Wagner kind of alluded, we'll be covering probability today, also be reviewing a little bit of stuff from last week's lecture, most notably some of the stuff around iteration, which we actually didn't get to, and then some of the stuff on conditionals, and then we'll just kind of jump into probability. And main announcements, so as usual, new vitamin, please complete that before Wednesday's lecture. Homework 5, due this Thursday, turn on Wednesday for bonus point, and then the final project 1, all of it is due on Friday, so please turn that in on Thursday for bonus point as well. And if you're working with a partner, just make sure only one person submits it. And yeah, just, please make sure the chat's open to everybody. Okay. So let's review a few things. So random selection, first of all. We kind of went over this a little bit. So this is basically how we can essentially, I guess, choose things randomly from a set of different outcomes. So we're going to be using this a lot in this class. And then the way it works is you use this function called np.random.choice, select things uniformly at random with replacement. So what that means is if you have, like, let's say you're randomly selecting something from like 3 different possible outcomes, when you select one outcome out of it randomly, you put it back in. And then when you select again, that way you still have 3 to choose from. So it's not like if you were to sample, if you were to do like a random selection of three times from this set of things, it's not like one time you take one out and then now there's 2 left. You always put it back in. So that's what with replacement means. And so you specify the outcomes that you're kind of randomly choosing from using an array. And you also specify how many times you want to randomly choose from this array. So by default, if you don't specify the number of times, you're just going to choose once, but you can also specify the number of times as well. And this is actually how the actual function is called. So pass in the array as your first argument, the sample size as a second argument. So let's actually just review this really quickly with an example. So let's say every morning there's kind of 2 main outcomes that you have in terms of what's going to happen. So either you're going to wake up or you're going to sleep in. So let's say I'm just going to define these different outcomes in a name called mornings. And then if we want to randomly select what's going to happen, we can do np.random.choice, pass in the array of outcomes. And so we get a random outcome here. And so if we run this multiple times, you can see how it kind of like changes up a little bit here. And so it's just kind of equally likely to pick either of these outcomes. So that's how it treats it. And then if we wanted to see, for example, your outcome every day for an entire week, we could do that as well. So you could do np.random.choice mornings and then pass in 7 as a second argument. And so now we'll get your entire week's worth of different outcomes for what you're going to do every day. All right, sorry guys. So Professor Wagner was coding up this function called happiness, and it's going to take in a decision. And so this is just an example of how we might use if statements. So let's say the decision is going to be kind of what you're going to do that morning. And so if the decision is wake up, then what we're going to do is we're going to return kind of the happiness score of what it's like to wake up. And maybe the happiness isn't going to be the same exactly, it depends on the day, how much you slept. So we're going to have some possible outcomes that depend on what happens when you wake up. So let's say the possible outcomes are between 4 to 6. So we'll define this as np.arange 4 to 7. And then we're going to return np.random.choice possible outcomes. So just randomly select something from the possible outcomes. So that's what happens if you wake up. And then if you sleep in, we write this as elif, so it's else if, decision equals sleep in. And so again, we're going to have some possible outcomes here, but they're going to be slightly different. So instead of 4 to 7, we're going to do 8 to 11. And well, actually 8 to 10, like 8 up to 11, which means 8 to 10. And then we'll randomly choose one of those outcomes. And so when we do that, what's going to happen is, depending on what decision equals, we're going to go into one of these lines of code. essentially. That's essentially what this function is doing. And so we can actually just try this out. So let's say we do happiness, or actually let me run this function. So if we call happiness on, let's say, wake up, it returns a score of 5. So how did it do that? Let's just walk you through that. So wake up got passed in and it got assigned to the name decision. And then Python said, okay, so if decision equals wake up, let's execute this code down here. It does, therefore let's execute that code. So what are we gonna do? We're gonna assign possible outcomes as this 4 to 6 array, and then randomly choose a number from 4 to 6. And then that's what it did. And then similarly, if we call this with sleep in, we can see now that we get a higher number. And why did we get a higher number? Because sleep in gets passed in here, gets assigned to decision. And then we check this first condition. So if decision equals wake up, in this case, it does not. That means skip all this code here, go to the next kind of control statement. And this is saying, okay, well, if now instead, if decision equals sleep in, execute this code. In this case, it does. So we do execute this code instead. And so in this case, I defined arbitrarily the possible outcomes to be 8 through 11. And so it randomly picked a number there. And so that's why we got 8. So if you run this multiple times, you'll see that the numbers change up. So this is 9, now it's 8. So these are like kind of both changing up a little bit here. And so these numbers I've defined are completely arbitrary. You can make them whatever you like. I just happen to say that when I wake up, typically my happiness is between 4 to 6. If I sleep in, my happiness is typically between 8 to 10. So that's just me personally. You might have your own numbers. So totally up to you. Cool. So now what we could also do is, we've been passing in a decision as a string. We could also pass in a random decision. Because remember up here, we had come up with a way to create a random decision. This was np.random.choice mornings, right? So we could actually just pass that in as well. So we could do kind of 2 sets of random things almost. So first you could say our decision to wake up or sleep, that's going to be randomly decided. And then our happiness is also slightly random as well. So we'll decide our happiness based on the decision as well. So this is kind of doing everything in one shot. So here we have decision equals a random decision. We pass in that random decision, determine what the random happiness is going to be based on the decision. So this is kind of a way to chain that. And so this is how we can kind of combine it all together. And then what if we wanted to know, like we wanted to simulate our happiness for several days throughout the week? If we wanted to do that again and again, it might be nice to actually write a function. So what we could do is we could create a function that does all of these 2 lines of code together again and again. So we could call this simulate one outcome. And then I'm just going to have it basically run these 2 lines of code. And we'll return happiness decision. So now we have a function, and I can just call this really easily now. And so I can do simulate one outcome. Here I get 10. Simulate it again, I get 4. So it's kind of, you don't get to see what the decision actually was here. You don't get to see whether you woke up or you slept in. But you do get to kind of go through the whole process of randomly simulating a day, essentially, and then seeing what the happiness is for that day. So now we have a way to do this. And then if we wanted to simulate 7 days, we could use a for loop. So I believe Professor Wagner just went over for loops. So we could do for I in np.arange 7. And again, for loops always act on an array. You need to have an array that you're going to iterate over. In this case, the array we're going to kind of iterate over is going to be np.arange 7, which means go from 0 to 6. So essentially go 7 times. And then what are we going to do each time? Like for each iteration of the loop, we're just going to call, we're just going to print out simulate one outcome. So now this prints out kind of the happiness scores for 7 days. So I'll stop for some questions here. What is I? So whenever you're doing a for loop, you have to, not only do you have to iterate over different elements of an array, you also need to assign them to something for each iteration. So in this case, we just assign the numbers 0 to 6 to the name I. And then we'll go like for I in 0 to 6. So basically in the first iteration, I equals 0. you do something based on I equaling 0. Then in the second iteration, I equals 1, you do something based on I equaling 1, and so on. So in this particular case, we didn't actually do anything with I. If you notice, like we said for I in this, but then this code here actually doesn't do anything with I. And that's okay. Like you can have code where you want to do something a certain amount of times, but you don't really care what the values are for each iteration of the loop. And so this is a situation where you might do that. If you actually wanted to print it out, you could do that too. So you could say for I and np.arange7, and then just put I there, and then it's actually going to print out what the value of I is. So this is showing you in the first iteration of the loop, I equals 1 equals 0, then I equals 1, and so on. So we assign I to what is inside the parentheses. No, so I gets assigned to each value in the array that you specified here. So here's another example. I think Professor Wagner might have already done this, but I'll just type it in again. So here's another way to do a loop. So you could do for day in make array, Monday, Tuesday, Wednesday. And you could just, for each iteration, for each element of the array, we're just going to print out the name. So we could do today is day. And so in this case, what's happening is, again, this for loop, what it's going to do is it's going to run through and execute the code that's written after the colon for each element of the array. So in this case, this array has 3 elements. So this loop is going to have 3 iterations. So in the first iteration of the loop, you assign Monday to day, and then you execute this code. And this code happens to use day, which is Monday. So then that's why it prints out today is Monday. Then in the second iteration, day is equal to Tuesday, and then execute the code assuming that day equals Tuesday. Then day equals Wednesday, execute the code assuming that day equals Wednesday. So that's essentially how a for loop works. And so there's different ways to do it. It's really kind of common to use I when all you're trying to do is just run something like the same exact code, essentially, like multiple times. So if you notice here, this code here doesn't even depend on I. It's just running regardless of what I is, but we just want to run it 7 times. So that's why I is just a short 1 character name. It's just convenient to write it like that. But there's no particular reason otherwise. Yeah, that's someone just mentioned I is the index in the loop. That's a good way to think about it. Cool. All right, so let's continue. So now we have a way to simulate our happiness score for 7 days, which is what we just did up here. But I want to also like maybe visualize these numbers like over a longer period, maybe make a histogram of these numbers. But in order to do that, I need these values in an array. So right now we were able to use this for loop to print out each individual happiness score for 7 days. But I'd actually like to be able to visualize this in an array. And I need to store these values in an array somehow. So we haven't been able to do that until now. And the way we do that is we append values to arrays. And so this is kind of how it works. So there's a function called np.append. And essentially the way it works is if you have an existing array, you can add another value onto it. So this allows you to kind of extend the length of an array. And so this is going to be very useful for things like for loops, and we'll show you why. So this is kind of the way you call it. So again, you have to have like an existing array already, and then you want to add, let's say, a new value to the end of it. That's what np.append lets you do. And you just make sure the value is the same type as the types you already have in the array. You can also take 2 existing arrays and then kind of stick them together to make 1 long array. That's also something you can do. We probably won't do that too much in this class, but it is something you can do. So if you have your new array is called array 2, it's going to be appended to the end of array 1. And once again, just make sure that the types are the same. So let's see some demos of this. So it makes sense. You know, what does this mean? Why would we want to use it? So let's start with a simpler example. So let's say we want to store outcomes over several days. So we always need to start with an empty array. So we're going to just call make array with parentheses, nothing inside it. That just means I'm making an empty array. So you can just see what this looks like. So you see here, it just shows array with like nothing inside. So that's how you make an empty array. And then let's say we simulate the first day is simulate one outcome, and we'll do outcomes equals np.append outcomes and first day. And then now let's look at what outcomes has. So now outcomes has 4. So how did this happen? Firstly, we simulated one outcome. We assigned that to first day. In this case, it ended up being 4. And then we appended 4 to this empty array outcomes. And then we have to assign it back into outcomes. This is also very important. So if you just called the line without this portion here, it's just going to return outcomes with 4 appended to it, but it doesn't actually update the value of outcomes. So we've seen some examples of this earlier in the class where there's some lines of code that don't actually modify the value that you care about. So very important here to assign it back into outcomes. And we get this. And then now let's say we had a second day that we simulate. So second day equals simulate one outcome. Once again, we could append the value of second day to outcomes. And now outcomes has 2 values. It has the 4 from the first day, and then now we've added a new value of 10 to it. And so just to give you a sense of what happens, let's say we did third day, and we try to do third day again, but we don't assign it back. So I'm going to just remove these lines of code here. So if we just call np.append outcomes third day, and then call outcomes, outcomes is still the same as before. So if you notice that something's happening where like your array isn't growing as much as you expect it to, it probably means you forgot to assign it back into that value. So that's really important. So let me stop for questions there as well, because this is super important. Can you do outcomes.append third day? In this case, you can't. You have to use np.append and then pass in the array, comma, the value you want to add to it. Where did the 4 come from? So the 4 was randomly generated. So this simulate one outcome, it simulates kind of our happiness for any particular day randomly. And remember, how did we define the happiness? Well, happiness depends on whether you slept in or woke up. And then based on one of those outcomes, you then randomly generate a happiness score depending on what outcome was. So that was like that big function that we made. And so in this particular case, happened to get an outcome of 4, which probably means that we woke up. And then on our second day, we got an outcome happiness score of 10, probably slept in that day. So that's kind of just randomly generated. Why was the third day not added? The third day was not added because I just called np.append outcomes, comma third day. But this line on its own doesn't actually update the value of outcomes. This line returns a new array that has the elements of outcomes with third day appended to it, but it doesn't actually get assigned to outcomes. You need to make sure to assign it. So if you actually want this to update, we need to write this. We need to add outcomes equals np.append. And then now you'll get a new value in there. And so again, these numbers are just coming from simulating the outcome for each day. So the first day was 4, that came from this line of code here, basically generated 4, assigned it to first day, then we appended first day to this empty array. That's how we got 4. Then we simulated another day, that ended up being 10, assigned that to second day, appended that to the array. Now we have 4 and 10 in here, and so on. Cool, so now we know how to append values to an array. We know how to simulate things with a for loop as well. So let's try to put all this together. So let's actually simulate our happiness for each day of a week. So we'll start out with an empty array, and it's going to be called outcomes. And this is going to just store our happiness for 7 days. So eventually this array is going to have a length of 7. Right now it has a length of 0. And what we'll do is we want to run something 7 times. So we'll do for I and np, a range 7. And then what do we do? What do you want to do in each iteration of the loop? We want to take outcomes and then append something to it. So we're going to do outcomes equals np.append outcomes. And what are we going to append? We're just going to append one random outcome. All right, so we do that 7 times, and then now we can take a look at what outcomes has. So here are now 7 randomly generated kind of happiness values for a week. And so essentially we just did the same code we did above where we were breaking it down line by line, but instead of just writing that same code 7 times, we can just use a for loop to do it a lot faster. So this just kind of saves us code. And we know that we're going to run the same thing every time. So it's very convenient to write it in this way. So we could do the same thing with the entire year. So let's say we wanted to know our outcomes for the entire year. We could do that too. So we could just take all this code, I'm just going to copy it, paste it down here. And then I'm going to change this to 365 instead of 7. So again, same thing we did above. We initialize outcomes as this like empty array, and then 365 times we're going to append a new random outcome. So at the end of the for loop, once it's all done, we should have 365 values. So we run this, now we have our kind of random happiness for 365 days. And then if you want to visualize it, we can do this as well. So we could do outcomes equals table with column. So we're going to take all those 365 outcomes and then put it into a table. It's just going to have one column in it. We're just going to call it happiness. And then we can visualize a histogram of all the values now using hist. So we'll do outcomes.hist happiness. Bins, let's just do np.arange 0 to 11, because your happiness is on a scale of 1 to 10. And so now we get a histogram of our kind of random happiness scores throughout the entire year, essentially. So any questions here? Do another one? Yeah, let's do it again. We can try it again. All right, let's simulate another year. So this was our first year at Berkeley. Let's try our second year. Okay. Try it again. Okay, so it looks pretty similar. Yeah, and the reason for that is basically it's not gonna actually change. Let me actually change these bins so you can see. I think it's doing something weird here. Ooh, I don't know what just happened there. Oh, you know what? I should do outcomes table. I shouldn't use the same name twice, sorry. All right, let's do this again. Here we go. So the reason it doesn't change that much is because the way it's generating these happiness scores, first of all, it's like kind of 50-50 chance that either you're gonna wake up or sleep in. And then within each of those kind of branches, there's like equally likely chance if you slept in that you're gonna get like 8 to 10. And then if you woke up, it's gonna be like 4 to 7. So overall, it won't change like too much. It's gonna be like mostly like flat for both of these, but there is some variability there. So if we like run another year, simulate again, it should look slightly different. So in this particular year, for example, we had a lot of values at 7, and we just do it again. Now we have more values at 4 and more values at 8. So you can see how it like changes up a little bit. Cool. All right. So I wanted to do another simulation, but we're like super short on time now. I think you guys get the idea, and you can look through the demo if you want to do like another example. We're using coin tosses, which is actually really helpful to see how that's done. But let's go to probability. Really want to make sure we cover that. So in this class, we're going to basically think of probabilities as just kind of the chance of some event happening. And so there's some basics here to cover. So firstly, the probability of anything has to be like at least 0. So you can't have like probably something as like negative. That doesn't make sense. So 0 is the lowest value. And what that basically means is if an event is impossible, then the probability of happening is 0. So for example, if I pick someone randomly in this like Zoom meeting right now, the probability they're from Mars is 0. So everybody here's from Earth. So that's something that's like impossible. And then conversely, if something is certain, the probability is 1. So if I pick somebody at random from this Zoom call and pick them out, the probability of them being from Earth is 1. So unless you're Elon Musk, you're probably from Earth. Okay, so those are the different values. And then we also have complements. So if an event has, let's say, a chance of happening of 70%, then the chance it doesn't happen is going to be 1 minus 70%. So this is true for any event. So like, if you have some event that you're thinking about, the chance of it not happening should be 1 minus the chance of it happening. So again, for example, let's say the chance of having like a first year right now in this Zoom meeting is like 33%, just making that up. So that means if I randomly pick somebody from the Zoom meeting and I look at what year they are, there's a 33% chance they're first year. That means that there's a 100 minus 33. That's the chance of the person not being a first year. So 67% chance of not being a first year. So that's kind of how we do that. Cool. So these are main probability basics. And this is actually, it sounds basic, but it's the most important one. And we always see mistakes on this on like tests. So if you're leaving the answer for probability of something and it's more than 100% or it's less than 0, there's something went wrong there. So that's like the first check. Always make sure it's like between 0 and 100. Has to be that. So no, you can't say like probably something is 110%. Like it's not a thing. Just 100. All right. So those are some ways to calculate probabilities. And then how do you actually like kind of calculate the chance of some event happening? So if you know that there's a bunch of different outcomes and they're all equally likely, it makes it a little bit easier to calculate. So if you have like, let's say 5 different outcomes and you want to know the chance of like one of them happening, basically you just count up the number of outcomes that make A happen and then divide by the total number of outcomes. So we'll see some examples of this right now. So here's like one question. So let's say we have 3 cards. We have Ace of Hearts, King of Diamonds, and Queen of Spades. So we have 3 cards, that's it. No other cards in our hand. And we just like shuffle the 3 cards and then we draw 2 cards at random. In this case, without replacement. So remember earlier we talked about with replacement. So in this case, what we're gonna do is we're gonna draw 2 cards without replacement. So what that means is I take my 3 cards, I shuffle them, I draw 1 card out, now I have 2 cards left. I don't put that card back in for my second draw. So for my second draw, I'm picking from the 2 remaining cards. And so basically you're guaranteed to get 2 different cards that way. And so the question is, what's the chance that I get a queen followed by a king? So basically I have these 3 cards. I draw, on my first card, I happen to draw a queen. And then on the second card, I have a king and an ace left. What's the chance then that I get a king? So basically what's the chance of all those things happening? So we can actually kind of write out all the different ways that it can happen. That can be one way to, that can be one way to figure out what the probability is actually going to be. Let me just add some space here. So let's actually write out all the different kind of combinations we could have of events that are happening. We know that we're drawing 2 cards without replacement from a stack of 3. So we're just going to list out all the different ways it could happen. So all the different ways, like anything can happen, actually, I should say. So like, for example, we could get an ace first, and then we could get a king. That's one outcome that could happen. We could get an ace first, and then we could get a queen. That's another outcome that could happen. We could get a queen first, and then an ace. We could get a queen first, and then a king. We could also get a king first, and then a queen. Or we could get a king first, and then an ace. So looks like there's basically 6 different ways that this is going to go down if you're going to take 2 cards out of a stack of 3. So these are all the different outcomes you could possibly get for those 2 cards that you draw. And so using the equally likely outcome idea, basically you just need to count up how many outcomes are going to result in the event that we care about happening, divided by how many outcomes there are total. So the number of outcomes there are total, well, that's just 6. We can see that here. And then we just need to count up how many outcomes give us the event that we care about. So the event we care about is queen first, followed by king. So if we look through this, there's only one outcome that actually gives us that event happening. So in that case, if we go back to the math in this equation on the previous slide, it's just going to be 1 on top. That's the number of outcomes that makes A happen. And then divided by total number of outcomes, which is 6. So probably this happening is 1/6. So someone asked a great question, which basically leads to what I was about to say is, this works really well. We can count up the number of different ways it's going to happen because there's just 2 cards that we're drawing out of like 3. So, this would be really complicated if you had a full deck of 52 cards. and you wanted to draw, let's say like 5 cards out of it or 10 cards out of it, there's like just so many combinations. I mean, it can be into like the millions. So it's not efficient to really like write everything out. So here's another way we can do it, which is a little bit more scalable when you have like larger values. You can actually break it down into steps. So what we can do is we can break down into steps what's going to happen in the first card, and then we'll break down what's going to happen, what's possible in the second card. So what we can say is in the first card, we know that we're drawing from these different options. It's going to be one of these 3 outcomes. And we need a queen to happen in the first card because it specifically said that what's the probability of getting a queen first followed by a king as a second card. So in this first card, we have 3 different outcomes, and we know that we want the one where the queen comes out. So I'm just going to put some brackets around that. So that's what we need to happen in the first card. So probability of that is going to be 1 out of 3. Why? Because there's only one outcome here that gets us the event that we want. And there's 3 total outcomes possible. So, okay, so we know that in the first card, probability is 1 out of 3. And then once we've taken that queen out, now we have 2 cards left. We have ace and king. And we want to get the king. So once again, we can calculate what's the probability once we're at this stage of getting a king. So in this case, it's going to be 1 out of 2. There's 2 cards. Only one of them gives me the thing that I want. So probability of this is 1 out of 2. And so now we know kind of the probability of each of these kind of on their own. And then the total probability is just going to be both of them multiplied. So, you know, we have the probability of getting a queen from 3 cards. That's 1 out of 3. Now that we know we have the queen taken out, the probability of getting a king is 1/2. And so the total probability is you multiply both the probabilities together because it's kind of 1/2 of 1/3 in terms of like all the possibilities that could have happened. So it's like 1/2 of the 1/3 of possibilities that could have happened. So that's why we get 1 out of 6. So you get the same math, same answer, but a slightly different way to calculate it. And this is going to be a really common way to calculate things when you have like a lot of different possible ways that they can happen. It tends to be a little bit more scalable. So this is actually, there's an actual rule around this. It's called the multiplication rule. So we'll just go over this. And basically the way it works is it says that the chance that 2 events A and B both happen is equal to the chance that A happens times the chance that B happens given that A already has happened. So that's essentially what we did. For us, A was getting a queen, and then B was getting a king after a queen. So in A, the chance of A happening, so the chance of getting queen from 3 cards that are ace, king, queen is 1 out of 3. And then what's the probability of getting a king as a second card, given that we already have the queen taken out, essentially? Well, that's just look at the probability of getting a king out of 2 cards, king and ace. And so that's 1/2. So that's one way that we can kind of break it up. And so what's interesting about this is that the answer, the probability of both A and B happening is going to be less than or equal to the probability of each of these 2 pieces, because you're multiplying 2 things that are less than or equal to 1. So the number is always going to be less than or equal to what the individual numbers were. So that's another thing to keep in mind. Like if you're answering a question or something like that, if you have 2 things that you're multiplying, 2 probabilities, the result should be less than each of the individual ones, less than or equal to the individual ones. So that's why we had like 1/3, 1/2, multiplied it, we got 1/6, which is even smaller. And intuitively, this makes sense because essentially it's saying the more conditions you have to satisfy, the less likely you are to satisfy all of them, right? So like just getting, if you just wanted to know like the probability of getting a queen out of, you know, your 3 cards, that's just like one condition. But then we also said not only you have to get a queen on the first card, you have to also get a king on the second card. So it's like more conditions to satisfy, which means it's less likely to happen. It's more difficult to happen. Cool. So that's the multiplication rule. And then let's do another question. So slightly different. So once again, I have 3 cards: ace of hearts, king of diamonds, queen of spades. I shuffle them. I draw 2 cards at random without replacement. So same exact setup as the last one. But now the event that we're interested in is slightly different. So in this case, we're saying, what's the chance that one of the cards I draw is a king and the other is a queen? And so here the order doesn't matter. In the first question, we said, what's the chance of specifically getting a queen first out of 3 cards and then getting a king second out of the remaining 2 cards. In this case, what we're saying is we're going to draw 2 cards in the same process. We'll draw 1 card. We have 2 left. We'll draw another one. So same exact process, but we're saying we just want to get a king and a queen. Doesn't matter which one comes first. So you could get a king first and then a queen, or you get a queen first then a king. So what's the chance of that happening? So intuitively, what do you guys think? Like, do you think the chance of this happening is going to be the same as the other one? Is it going to be more? Is it going to be less? What do you guys think? You don't need to give a number. Just curious what you think. Like, do you think that this is going to intuitively be like harder to happen, more easier to happen? Okay, nice. Yeah, so most people seem to be saying easier to happen. So yeah, it is going to be easier intuitively. Why is that? It's because the other one was a stricter condition. The other one was saying you're going to get a king and a queen, but it's very specific. Queen needs to come first, then king needs to happen. In this case, it's saying, I don't care what the order is, just give me a king and a queen. What's the chance of that? So there's kind of more outcomes that are going to lead to that. And so we could actually answer this kind of writing out the different ways that it can happen. So essentially in this case, there's 2 ways that this can happen. So I'm just gonna write this out. And so we'll go through one way that it can happen and another way. All right, so the first way that it can happen is you get the queen on the first card and then you get a king on the second card. So we kind of went over that already, but basically in your first step, you have ace, king, queen. So we need to get the queen. And then now we have 2 cards left and we need to get the king. So we already kind of talked about this way before. So we talked about how the probability of getting the queen in the first card, that's 1/3. Probability of getting king in the second card, that's 1/2. And then the second way that this event can happen is that you draw the king first out of the 3 cards. And then in the second step, when you have 2 cards left, you draw the queen. So we can write this out similarly as well. So first step, we get the king instead of the queen. What's the probability of that happening? It's 1/3 again, because you're picking 1 king out of the 3 cards that are there. And now we have 2 cards left. We have the ace and the queen, and we want to pick the queen here. And what's the probability of this happening? It's 1/2, because we have 2 cards and we're picking a queen out of it. And so essentially there's 2 different ways that this event can happen. And when you have 2 ways that an event can happen and they are like 2 distinct ways, like there's no way that they can both happen together. Like there's no way you can get a queen first and then a king, but also get a king first and then a queen. Like that doesn't make sense. It's like one of these is going to happen or the other. Then you can add up the probabilities. So that's when you can add up probabilities. So the probability of this first way of it happening using the multiplication rule, it's going to be 1/3 times 1/2. And then we can add to it the second way that can happen. And what's the second way that can happen? Well, it's also 1/3 times 1/2. So we can write this out. And so in this case, we get 1/3. That's kind of the answer here. And so this is called the addition rule. And so why did we add 2 probabilities together in this situation? It's because we had an event where we knew it could only happen in exactly one of 2 ways. And so when that's possible, then you can add the probabilities together. And so in this case, the answer is going to be greater than or equal to each of the individual chances. So we talked about how the first way, which is like get a queen first and then a king, that has probability 1/6. The second way, which is getting king first and then a queen, that's also 1/6. So each of these was 1/6, but then when you add them together, you get 1/3, which is more. And when you add 2 probabilities together, you always get something that's greater than or equal to. That's because all probabilities are greater than or equal to 0. So the probability should never go down if you're adding 2 probabilities together. But the main distinction here is that, we had 2 different ways for this event to happen. That's why we're allowed to add things together. Whereas if we go back to the multiplication rule, in that case, it's not 2 different ways of something happening. It's actually like this thing happening depends on this first thing happening. Because we said we want a queen to be drawn first, and then we said what's the probability of getting a king given that a queen has now been taken out. So there's a dependency there. And so that's why we multiplied here. And essentially it's because B happening was like depending on A having already happened. So that's kind of the main thing to make sure. Okay, and then lastly, let's go over the complement rule. So we mentioned this really briefly, which is basically talking about how, if you have probability of some event happening, the probability of it not happening is just 1 minus that. And so let's see an example of why this is actually useful. So for example, let's say you have a coin, you're going to flip it 3 times, and you want any outcome except for tails, tails, tails. So that's like, you want to see what's the probability of getting something, without tails, tails, tails. So calculating the probability of not getting tails, tails, tails is really hard because there's so many different ways that this can happen. You could get like 2 heads and a tail. You could get 1 head and 2 tails. You could get all heads. And then even the one where you get like 2 heads and a tail, they could be completely different orders. Like maybe first you get a tail and then 2 heads, or maybe you get 2 heads and then a tail. It's just like crazy. It's like way too many ways. It's just too complicated. So let's just use the complement rule because we know that the probability of calculating tails, 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 if we believe that's a little bit easier to calculate, then let's just calculate that probability and then do 1 minus that. So it makes it a little bit easier. And so in this case, the probability of getting 3 tails in a row, that's going to be equal to the probability of kind of each of the heads multiplied together. So basically, probability of getting tails on the first head, that's going to be 1/2, times probability of getting tails on the second head, given that we got tails on the first head. In this case, it actually doesn't depend on what happened. It's still going to be 1/2. And then multiply once again the probability of getting tails on the last head, given that you already got tails the first 2 times. It's still 1/2. The coin doesn't really change depending on what we got so far. And so if we write this out, it's going to be basically 1/2 times 1/2 times 1/2. So the probability of getting 3 tails in a row, that's 1/8. So now that we know that, the probability of getting at least 1 head, or same thing as basically probability of not getting 3 tails in a row, is just going to be 1 minus that number. So 1 minus 1/8, which in this case gives us 87.5%. So that's kind of how we can calculate that a little bit easily. And then we can extend this to an even harder problem. So let's say you're doing 10 tosses and you wanted to know what's the probability of getting at least 1 head in 10 tosses. So basically find the probability of getting all tails and then just subtract that from 1. So in this case, it turns out that getting all tails is 1/2 raised to the 10th power, because you just do 1/2 times itself 10 times. And that's a really, really tiny number. So 1 minus that is like almost 100%. In this case, like almost 99.9%. So basically what this is saying is like in 10 tosses, it's like almost impossible to not get at least 1 head. Not completely impossible, but almost possible. Why is it to the 10th power and not the 9th power? Because you're first calculating what's the probability of getting tails for all 10 tosses. So that needs to be 1/2 times itself 10 times, just like we did up here for 3 tosses. That's why it's 1/2 to the 10th power. So you need to make sure you're getting tails for all 10 of them. That's kind of the event that we're going to find the complement of. So it turns out that basically getting at least 1 head, the complement of that is getting no heads. And so the probability of getting no heads, that's the same as the probability of getting all tails for the 10 tosses. That's why we do 1/2 to the 10th. What would it be for 2 heads? Oh, probably getting at least 2 heads. Yeah, so that gets a little bit trickier. You'd have to calculate like the probability of, maybe getting like at most 1 head and then take the complement of that. That might be the easier way to do that. But even that's gonna be a little bit challenging. But for this class, this is kind of the extent of how difficult the probabilities will get. So we won't do anything like super fancy beyond this. So as long as you can kind of do these main examples, that's the main thing to keep in mind. It's like, when do I multiply probabilities together? When do I add them together? Just try to understand that really well. And then just know when taking the complement sometimes makes the math a little bit easier for you. And so this is an example of that. If you've never taken AP stats, I think you'll still do okay. You'll be fine. You do not need AP stats for this class. Okay, so we're definitely over time. I'm just gonna stop the screen share, but we'll stay on for questions for sure.
And a brief announcement, vitamin 14. The second question is buggy, alas.